we've already started to deal with digital signals in the last lab, but we are going to have to get a little bit more in depth now with digital signals. So I thought I'd start to lecture on them from a theoretical perspective. So we'll back up, talk about digital signals a little bit. Then we're going to talk a little bit about logic and logic gates in the next lecture. We're going to use a couple of them in this lab, this week's lab, so Lab 5. And then then we'll talk about how, so next week we'll talk about how to sample a signal, a continuous signal, and make it turn into a digital signal and do discretization. But for now, we'll just talk about them, and then analog signals, digital signals. We'll talk about how to go from one to the other next week. So, a digital signal is a continuous signal transmitted with the assumption that the receiver will interpret it as representing a finite number of values. Okay, so a signal is a signal. You can't send a voltage that's not a continuous voltage. They're all in reality analog, right? They're all continuous voltages, but it's one that's intended to be, a digital signal is one that's intended to be interpreted as being one of several values. Typically, only two values are represented. Binary 1 or 0, also called Boolean true and false. Okay? So, depending on what level the signal is, we're going to interpret it to be either true or false, 1 or 0. Okay? That's most digital signals are of this type, of this Boolean true or false type. Digital signals are the signals of digital circuits, of which CPUs, memory, reading and writing devices, and I/O devices are made. So when you're working with computers, you're working with a lot of digital signals. There are, of course, also analog voltages involved with some of these devices, and they might be interpreted as analog. But the vast majority of computer signals are digital signals. Continuous or analog ones are an exception to the rule. It's rare. There are certain applications where you would use an analog signal, including in our case where we're interested to have an analog input sometimes or an analog output sometimes. We have digital inputs and outputs, but analog sometimes is what we want. We want to measure how much voltage is at this terminal in our circuit. So why would one want to discard the potentially infinite amount of information resolution in a continuous signal? Okay, so it's kind of weird, right? We were like, I've got this signal. I could represent, so say even from, if you had 0 to 5 volts, say, you could represent, it could be, if it's, continuous between 0 and 5, there are an infinite number of levels you could have that voltage at. So in theory, you could represent all of the information in the universe in a continuous signal from 0 to 5 volts, right? Akara would be 3.07298 yeah. That would be the voltage that represents you, and then
an ID.
So
ID.
right. I have dibs on pi. I'm calling dibs. So why would we do that? We have all this infinite resolution. Why would we do away with that and just say it represents either true or false, which is way less information that you can represent. So primarily because one, often our transmission, which we'll often just denote as TX, has a limited number of potential values, especially when dealing with data stored as a computer memory bits. So in computer memory, you can only store it as 0 or 1, right? In most computer memory. So in each bit, it's either going to be a 0 or a 1. So when you transmit that bit, there's not a lot of, it's not very useful to be able to represent an infinite number of things with that signal. Representing just 2 things is sufficient. So that's one reason. And 2, noise. So offsets or biases and random signals added to the transmitted signal through a number of mechanisms. So when you transmit a signal, you lose some of that ability to have a lot of different representations because you're going to have noise and the signal is going to wander around. Anything that is, so anytime you have a circuit that's at a non-zero physical temperature, you're going to have noise. So you can go through an interesting derivation of this, but it's called Johnson-Nyquist noise in a resistor. So and a wire has some resistance to it, right? You're going to have some voltage fluctuation if it's at non-zero temperature, just from what they call thermal noise. There are other noise processes too, and so sometimes noise will come in from some background electromagnetic field. So you could be close to something that's transmitting and your circuit might pick that up. You could be getting electrical signals coming in through electronic ways to your circuit, like especially it comes through power supplies a lot of times, like so you're powering your circuit somehow. That comes from, usually eventually it comes from a source that is the AC line, and there's all kinds of noise in that. So cleaning that up, you can only do a certain amount of cleaning up of that signal. If it comes from a battery, it's by far the cleanest electrical signal you can get from a source, from a battery. But there are still different ways that noise can come in. You can't get rid of noise, you can only make it small. So noise coming in is a huge part of why we can't have good fidelity to, so like for instance, if I was represented by the number pi and then Akara was represented by the number pi plus 0.00001, telling the difference between us in number would be very difficult because we have this fluctuation in voltage that's probably greater than 0.0001 in most cases. So with noise, we lose significant resolution, and a trade-off emerges between voltage resolution and fidelity. Throughout the history of digital electronics, the tendency has been to sacrifice voltage resolution, settling for binary encoding, so just 1 or 0, for time resolution. Digital electronics can send and receive digital signals that can switch between 0 and 1 at blazing speeds. So that's been the sort of the saving grace of digital electronics. Yeah, you can only represent a 1 or a 0, but you can change which one you represent really fast. So you can send a lot of bits really fast. And as we've talked about, you can encode a lot of information. When you start to lengthen the number of bits, you get 2 raised to the power of the number of bits worth of things you can represent. So that's been by far the primary way digital electronics have evolved. Is like, okay, we're just going to stick to binary for the most part signals, and we're going to just switch back and forth between those and transmit a lot of information very quickly. So that's the idea. A number of digital signal standards have been developed, with the CMOS, complementary metal oxide semiconductor, or CMOS standard being the most popular. So a lot of computing stuff is in CMOS. But several others remain in use, including the transistor logic, or TTL standard, which is now described. We'll talk about TTL, but fortunately, we don't really lose any generality. We talk about TTL. It's one standard, but they're all similar. So we'll talk about TTL, but they all are, they have different value, different levels of voltage ranges and all that, but they're all very similar. So if you understand one, you understand the idea of them all. It's just knowing like what the levels are for that specific standard. With reference to figure 4.3, so look at this figure. Is that not a pretty figure? I love that figure. It took me a while to make it, but I was like, worth it. It's so nice. Okay, so with reference to this figure, the TTL standard defines interpretations for voltage level ranges for both transmission output and reception input. So let's look at that. On the left-hand side, I've represented, okay, this is a transmitter, signals coming out. And so there's a standard, the TTL standard defines acceptable output, transmission ranges of voltage to represent different values, and then acceptable input ranges as well. So in order to be compliant with the TTL standard, your device should use these. So for output on the left-hand side, output ranges here, notice there are 4 important ones, 0, 0.4, 2.4, and 5. So when you have a 1 as your output, so when you want to represent true, so that's this one here, 1 on your output, then the right ways hatch, so between 5 volts down to 2.4 volts is considered a true voltage. So when you're outputting it, if it's between 2.4 and 5 volts, you're transmitting a true. Okay. So this signal, this blue line here, that's noisy. In this region here, it's clearly true, right? It's 1. So transmitting as a 1, that meets the standard just fine. And if it's going to be a valid TTL false or 0 output, then the right hatching down here says 0 to 0.4 volts is the standard there. So as long as you are between 0 and 0.4 volts on your output, that's representing a 0. So good. If you are in this region here between 2.4 and 0.4 volts, that is an undefined voltage level. It's neither true nor false. And a TTL standard compliant device probably will make no promises as to what it'll do with that. So the idea is you don't want to be there. That's no man's land. Just don't be in between those two. Yeah. Now, on the receiving side, so on the input or receiving side, which is the right. So on the right, I've shown a receiver. So now we're on the right-hand side of the graph. We're looking at these ranges. So from 2 to 5 volts, we have a valid true, a valid TTL1 signal. So notice that's a little bit bigger than the output range. So it's still up to 5, but it's down to 2. So we've got a little bit of padding here. So you could send something at 2.4, valid, and it could wander down here to 2 volts for an input. That's considered valid. That's fine. It's because a lot of times noise will be introduced in the transmission between transmission and reception. So we have to give a little bit more margin there. And in fact, this is called the noise margin. So this difference here is called the noise margin. And the same is true for the 0 or the false signal as well. So you have, in this case, it's symmetric. So there's a 0.4 volt noise margin on this side too. So if you transmitted a 0.39 volt, which was valid for an output, and it wandered up to be like a 0.7 volt, you would still be a valid false digital signal. Another thing to note is that, so what happens if there's a voltage that's transmitted that's above 5 volts or received that's above 5 volts? And they won't usually talk a lot about this for a device. Like they're going to say, oh, 5, that's the max. But most of the time, anything above a 5 up to a certain point is fine and they'll be interpreted as true. But the TTL standard doesn't guarantee that. So with many devices, though, if you received 6 volts, still would come in as true. And the same on the negative side, you can go negative usually, and it'll translate to false. To a point. Sometimes there's a certain level that you can either damage the device or you can maybe get some weird behavior from it. So it's best to not go too far out there, but sometimes you're fine still. Which does make it so that a 5 volt, 0 to 5 volt range for a digital signal is pretty common, but there are other voltage ranges as well. But sometimes you can use a digital signal from one standard, like a CMOS and a TTL together, and sometimes things will still work. You got to be a little careful. And actually, our Myrios, I think, use their own, I forget what the level is, but they have a level. It's like their own National Instruments digital level standard, which is kind of annoying. But yeah, so I am the TTL one actually is very common for desktop instruments in a lab. So the like triggering an oscilloscope, a lot of times it's TTL signal. It's pretty common. So we use TTL in this lab for some of the logic that we're going to do. So, where were we? Yeah. Okay, I think I covered all of that. In addition to voltage specifications, the TTL standard includes current output and input ranges. So we're just talking about voltage levels for the signals, but if you want to get into, if you're going to design a device that's TTL, you need to worry also about current. When you're just working with a bunch of TTL devices, typically you just think about the voltages, and that's all you care about. So furthermore, it specifies the maximum time for a TTL compliant device to switch between a 0 and a 1. So that's another part of the standard. In lecture 4.3, so the next lecture, some building blocks of digital circuits are described. How analog signals are converted to digital and vice versa are explored in lecture 4.5. So that'll be next week. Any questions on digital signals in general? Pretty fun. Of the types of signals, digital's like my top 2, definitely. Yeah.